So far we've looked at scalar images with convolutional kernels that have a certain spin behavior. That is to say, rotational equivariance by virtue of the complex exponential form for the angular component of the kernel. Now, the kernel itself is said to have a certain spin behavior for reasons that will become clear in probably about the next 10 to 20 slides. What I mean by the spin behavior is really just the angular frequency m. Now, in order to make this make sense in a physics perspective, let's consider going beyond just images to do convolutions on, and do convolutions on more interesting physically realistic systems that have vector and tensor properties associated with them. So for example, rather than just considering a scalar image with scalar pixel values or a continuous scalar function, let's now consider something like an elastic sheet. That elastic sheet can have a scalar field associated with it. For example, the temperature at every point in space in the sheet, that's a scalar field. It can also have a vector field associated with it. For example, the displacement vector at every point in space. If the sheet has been stretched a little bit here and stretched a little bit there, at each point in space in the sheet, we can associate a vector that says how much that sheet has moved from its equilibrium position. And it's not just a magnitude, we need to specify the direction in which it was stretched, so that's a vector field. We can also define a tensor field. Again, at every point in the sheet, we can look at the stress tensor. The stress tensor is really all about saying how much different segments of the sheet exert forces on each other and in which directions. And for each point in the sheet, we can associate all three of those features at the same time. So in practice, for a machine learning pipeline that's designed to learn those kinds of features, we would want to concatenate those three features into one single feature vector. So the temperature, the displacement and the stress tensor all into one single feature vector. And looking at it from this perspective will really help us to unify what we mean when we're talking about tensor products of spin fields, which is the language I used earlier. So that's what this section is all about. It's all about trying to make that language of physics make sense in the context of convolutions, so we understand how to do convolutions on physical systems. Now, let's go ahead and look at the actual transformation properties of certain physical features. So let's start with the transformation of the scalar field, the temperature. Well, if I've got the temperature at some point P, and I rotate the sheet, rotate the image if you like, in the language of the previous slides, then what we want to know is what is the temperature at the new point, Q alpha of P. That is to say, at the rotated point, what's the temperature? Well, it's exactly the same, right? So the temperature itself, it's a scalar, and it's just that the sheet has moved from there to there. So the temperature itself is not going to have changed. And algebraically, I'm going to express it using this language here. So T superscript alpha just means the temperature at the rotated point alpha. And I'm also using Q subscript alpha P to denote the fact that the point P at which the temperature is being measured has now also been rotated. So it's not two rotations, it's just a notation used to denote the rotation. Okay, so that's a pretty trivial transformation behavior. But let's look at something slightly more interesting. Let's look at our displacement field. So remember, it's a vector field, and that means that at any point in the sheet, which we can point to using the vector P, there's going to be another vector, and I'm going to call it U of P, which represents the displacement field at that point. So if we now rotate the sheet, well, the vector U also rotates, and so we want to know, generally speaking, what the transformation law is that describes this. It's pretty simple. So the way to think about it is that Q alpha of P, which is this point here, that is to say it's the rotated vector Q alpha of P, plus U alpha of Q alpha of P, which is the displacement vector that has itself been rotated. Well, that is found by just taking the original P plus U of P, which is the original P vector and the original U of P vector summed together, which gives you that dotted line, then rotated. So take the dotted line at the bottom and rotate it up to the top, and you get the same thing as if you add together the vectors Q alpha P plus U alpha of Q alpha P. Okay, I hope that makes sense. But if you just look at it, it's very geometric, very intuitive, just sort of looking at it. So then we'll just distribute out the right-hand side, and just by disregarding the rotation q alpha of p on the left and right hand sides, we obtain the transformation law. Why is it that we're able to discard q alpha p on both sides? It's basically because it doesn't matter where the u vector is. If you have a vector that emanates from this point and you have this as your coordinate origin, it doesn't matter where this vector starts. Its rotation properties are always the same. So the fact that it's attached to the end of point the vector p doesn't matter, and that's why those two terms cancel. Now finally, the tensor transformation property. In order to define the tensor transformation property, we need to use an intermediate device, the traction vector. The traction vector basically just tells you how much, for a given line segment drawn through the material, how much this side of the material is pushing on or pulling on this side of the material. So it's like the traction between the two sides defined according to some line segment. And that line segment has a normal vector associated with it. And the traction vector is just defined as the stress tensor represented as a matrix multiplied by that normal vector, where we use a matrix multiplication. That's a useful way of looking at it because it means that we can write down our transformation laws and actually derive the tensorial transformation law geometrically and therefore, quite visually. So the first thing to do is just to see that our normal vector n just transforms as a vector, just like the displacement vector did in the previous slide. The same is true for the traction vector because it's just a vector, right? So exactly the same transformation law. But we can then substitute in the definition of the traction vector t in this right hand side here. So you can see that we'll just write q of alpha t of p is equal to q of alpha of sigma p of times n of p. And so that then allows us to, we can then compare it with this alternative way of writing down the traction vector. So we can write down completely independently as a separate line of reasoning that the traction vector at the rotated point p is just equal to its original definition as up here, but now I'm just using the rotated definition of sigma and the rotated definition of n. Okay, so here I've got sigma alpha q alpha p. That's just the stress tensor at the rotated point, and we've got our normal vector again at the rotated point. And so by comparing that definition with this result, we can then equate those two right hand sides and we're nearly home and dry. So it's just a bit more algebraic manipulation to get us home. We just firstly need to remind ourselves of the transformation properties of the normal. It's already up there on, I think, line 2, but we're going to use it now because we want to say that for all possible values of that normal and whatever possible line segment we wrote down, we can say that this relationship is always true. So we'll substitute n alpha of q alpha p on the left hand side for q alpha of n of p by using that transformation law, and then we can just get rid of the normal vector because this relationship is always true irrespective of which normal vector you choose. So we're nearly there. We just multiply on both sides by from the right by the transpose of q alpha, and that is then the transformation law for the stress tensor. So in summary, we've got our scalar field, our vector field and our tensor field, and the formal transformation properties for all three.